Welcome back, guys. Today we're going to be looking at topic 7.4, which is all in relation to the volume of 3D objects. All right, so first of all, again, reviewing those shapes, we have a triangular prism. Notice it's a prism because it's got two of the same shapes on both ends, and then it's separated by rectangles. We have a rectangular prism. A cube is just a fancy or special case for a rectangular prism, meaning all of the sides and faces are the same. Pentagonal prism, again named after the shape of the face, and a hexagonal prism. So we're going to look at volume of prisms first. Now, volume is how much space an object takes up. So with surface area, we're looking at how much material we need to cover an object or how much paint we need to paint a surface. With volume, we're looking at how much space an object actually takes up. So looking at three examples here, we have a rectangular prism and we know the area of the base is 40 and the volume is 160. For the triangular prism, the area of the base is 24, the volume is 96. And for a cylinder, we have an area of a base of 50.3 and the volume of 251. Now the question is, what is the relationship between the area of the base, the volume, and the height? And the answer is, for a prism, the volume is the area of the base times the height. And so I can give you a lot of the formulas for rectangular prism and triangular prism and cylinder and so on, but I can't give you every formula that's out there. So if you come across a trapezoidal prism or a hexagonal prism, you need to know that the formula is just the area of the base times the height. So if you know the area of a trapezoid, you can multiply by the height and you have the volume of the trapezoidal prism. And so if we were talking about the volume of a rectangular prism, this is going to be length times width times height, because the base is a rectangle. Rectangle is length times width. Area or the height is height. For a triangular prism, technically we can refer to this as 1/2 base times height because it's the base of the triangle times the height of the triangle. And then we have to multiply by the height of the prism. And so it's going to be height 1 and height 2. Some people will also think of it about this as volume is length times width times height divided by 2. All right, so it's the area of the triangle times the height of the prism. And then for a cylinder, volume is pi r squared times height. Area of the base is a circle times the height. So for a cylinder, the volume is pi r squared times height. So it's still area of base times height. Again, we just give it a special name. All right, so let's take a look at the first object here. So we're asked to find the volume of the trapezoidal prism. Now with the trapezoidal prism, again, we have to find the area of the base, so that means it's going to be a trapezoid, and then we multiply by the height. Now, sometimes when we're given an object, we're given distractors, and so we have to think about what numbers are the most important. If we're looking at the area of a trapezoid, we need to know the 10, we need to know the 4, because this is also 4 right here. We need to know the height of the trapezoid. Then we also need to know the height of the prism. So the 3.6's here are actually just distractors. They would come in handy if we were doing surface area of a trapezoidal prism, but we don't need it for volume. So in order to find the volume of the trapezoidal prism, where it's going to be the area of the trapezoid times the height of the prism. So we're going to start with our trapezoid. I'm just going to redraw it here. We have our height of 2, and then we've got 4 and 10. So the volume is going to be the area of the trapezoid. Now, an area of a trapezoid is 1/2 times a plus b times the height of the trapezoid. So I'm going to call that height 1 times the height of the prism. I'm going to call that height 2. So volume is going to be 1/2 times 4 plus 10 times the height of the prism, the height of the trapezoid, which is 2, times the height of the prism, which is 7. Putting that all into my calculator, we get 98 centimeters cubed. Now, typically, I'll probably ask you to round to the nearest tenth, so you could also write that as 98.0 centimeters cubed. Now, unless you're told specifically how to round, I'm not really going to worry about rounding, but I will worry about units for sure. All right, so take an opportunity maybe to pause the video here, try these questions on your own, and then we'll come back and check the answers. All right, so this first example here is a cube. So we can think about a cube has, or when we think about the formula for a cube is going to be side cubed because all of the sides are equal. So volume equals side cubed, so volume equals 8 cubed. Volume is 512 feet squared. Now, or sorry, 512 feet cubed because we're talking about volume. Now you could also look at this as just a rectangular prism, so length times width times height. Volume would be 8 times 8 times 8, which is still 8 cubed, and that gives us 512 feet cubed. All right, taking a look at our next example, we have a cylinder. Volume of a cylinder is pi r squared times height. Volume equals pi times 2 squared times the height, which is 6. A volume equals 75.4 centimeters cubed. All right, now let's take a look at our triangular prism. So again, the volume of a triangular prism, area of the base, which is a triangle, so 1/2 base times height, and height of the prism. Again, you can also think about that as just length times width times height divided by 2, which is often what I do when I'm doing a calculation. I go length times width times height divided by 2, because ultimately a triangular prism is just half of a rectangular prism. So if a rectangular prism is length times width times height, a triangular prism will be length times width times height divided by 2. Either way, you're still going to get the same answer. So I'll use the first formula this time. 1/2 times base, which is 4, times the height of the triangle, which is 2, times 6, and that gives us 24 feet cubed, or 24.0 feet cubed if we had to round to the nearest tenth. All right, now the next example is a composite shape, or a composite object. In other words, it's smaller objects put together to make a bigger object. And so what we're going to do is we're going to calculate the volume of one rectangular prism, and then we're going to multiply by the number of rectangular prisms we have because they're all the same size. Now, if this length here is 1.5, that tells me that this side right here is 0.5, or 0.5. So the volume of one of these rectangular prisms is going to be 2.2 by 0.5 by 0.5 here as well. So my volume of the entire object is going to be length times width times height times 6, because if we count, there's 1, 2, 3, 4, 5, 6 rectangular prisms. So the volume is going to be 2.2 by 0.5 by 0.5 by 6. And 2.2 times 0.5 times 0.5 is 0.55 times 6 gives us 3.3 meters cubed. All right, so we're going to talk about prisms and pyramids. Now, when we think about prisms and pyramids, there's actually a correlation between the two when it comes to volume. So I want you to take a look at these objects here. We have a rectangular prism, rectangular pyramid, same base, same height. Cylinder and cone operate the same. Remember, we're going to treat a cylinder like a prism, and we're going to treat a cone like a pyramid. And then we've got another example of prism and pyramid. Now, normally in class, what I do is I grab these objects. I grab a rectangular prism, a rectangular pyramid. They'll have the same size base and the same height. And I'm going to fill up the pyramid with water. And I'm going to ask you, how many pyramids of water would fit into that prism? So if I were to fill up this rectangular pyramid with water and start pouring the water into the rectangular prism, how many pyramids would it take to fill up that prism? Just think about what your answer might be. I could do the same with the cone. How many cones would fit into a cylinder? How many pentagonal pyramids would fit into a pentagonal prism? And most often the guess I get is 2, but in fact it's actually 3. So 3 pyramids fits into one prism. So think about that. If the volume of a rectangular prism is length times width times height, the volume of a rectangular pyramid is going to be length times width times height divided by 3. So it's 1/3 the size of a prism. If the volume of a cylinder is pi r squared times height, the volume of a cone is going to be pi r squared times height divided by 3. All right, so let's take a look at some examples. All right, so we've already talked about the relationship between a prism and a pyramid. If we're talking about the volume of a pyramid, the volume is going to be the area of the base times the height divided by 3. Now, we don't want to mix that up with triangular prism. Triangular prism would be length times width times height divided by 2. But if we're talking about a pyramid, it's going to be length, a rectangular pyramid would be length times width times height divided by 3. So it's really important that you take advantage of your formula sheets that have most of these formulas on them. Volume of a cone is going to be area of base times height divided by 3. Well, the base of a cone is pi r squared times height, and we're going to divide by 3. All right, so let's take a look at some practice questions here. Now, when we're dealing with a pyramid and we're talking about length times width times height, we're talking about the perpendicular height. So the perpendicular height goes through the center of the pyramid. This one on the side here is called a slant height, and the slant height is only used for surface area. That being said, sometimes for pyramids and cones, I will not give you the information you need directly. You'll actually have to use Pythagorean theorem to find the missing information. All right, for this example, we're looking at a rectangular pyramid. If you get an object that I have in a question and I've just labeled 16 here and nothing on the side, you can assume that these are the same. So in other words, a square-based pyramid. So if I had to do surface area, I'd actually be creating a net, unfolding my pyramid, and finding all the areas of the faces and adding them up. But we're talking about volume, so we're looking at how much space the object takes up. So the volume of a rectangular pyramid is length times width times height divided by 3. So volume is going to be 16 times 16 times the height. So we want the perpendicular height, which is 15, divided by 3. Putting that into my calculator, I have 1,280 inches cubed. Now again, if I had to round to the nearest tenth, I'd have 1280.0. All right, so we're going to take a look at the volume of the cone. So when we're talking about a cone, we're looking at the area of the base being pi r squared. The height of the cone is height, and because it's a cone and not a cylinder, we're dividing by 3. So our volume is going to be pi times r squared, r being half of 25, so 12.5. So pi times 12.5 squared times the height, which is 40, all divided by 3. Putting that into our calculator, we get 6,544.98 centimeters cubed. If I had to round that to the nearest tenth, it would be 6,545.0 centimeters cubed. Because the 9, if I have to round to the nearest tenth, the 9, when I look at the 8 tells me I have to round up the 9. That makes it a 0, which causes a chain reaction and makes me round up the 4 to a 5. So if I had to round this number to the nearest tenth, I would have 6,545. All right, let's take a look at our next example. It says many of the operating costs of a greenhouse depend on its volume. For example, the energy used to heat a building depends on the volume of the building. The two large greenhouses at the Mud Art Conservatory, this is in Edmonton, have square bases measuring 26 meters on each side. The apex, in other words, the point of each greenhouse, is 24 meters high, and we're asked what is the volume of each greenhouse to the nearest cubic meter. All right, so I'm going to do a quick sketch here. We know that our sides are 26 meters by 26 meters. And we know that our height through the center is 24 meters. So our perpendicular height is 24 meters. Now, volume is going to be length times width times height divided by 3. So 26 times 26 times 24 divided by 3 gives us 5,408 meters cubed. Now, if I had wanted to calculate the surface area of this pyramid, or if I wanted to ask how much glass is needed to glass is needed for these pyramids, then I would be doing surface area. And in this case, I would have to find the area, the area or the surface area of each of the triangular lateral faces. So the sides of a 3D prism or 3D object are called lateral faces. I'd have to find the area of each of those faces and add them up. I would not have to include the bottom because there wouldn't be any glass on the ground. All right, taking a look at our next example, we're going to look at volume of a sphere. Now, just like there's a correlation between prisms and pyramids, or cones and cylinders, there's also a correlation between cylinders and spheres. So again, in class, I usually do a bit of a demo, and I use this one with a video. So I'm going to post the video on Google Classroom in case you're interested in watching it. But what you'll see in the video is that a sphere, if we have a sphere with the same height as a cylinder, a sphere is actually 2/3 the size of a cylinder. And so again, if you want to watch the demo on that, I've got a video that I will link in to our Google Classroom. But breaking this down, you do not have to know how to derive the formula, but I just want to show you how they do correlate. If I know that the volume of a sphere is 2/3 the volume of a cylinder, and we know the volume of a cylinder is pi r squared times height, 2/3 times pi r squared times height will give us this formula here. Now, if you notice off to the side, height is 2 times the radius. And if they're the same height, that means the height of the cylinder is also 2 times the radius. So I can replace my height with 2r. Now, using what we know from exponent laws, when I multiply this out, 2 times 2/3 becomes 4/3. Pi is pi, and r squared times r to the 1. Remember our exponent rules, 2 plus 1 is 3. So 2/3 of a cylinder is 4/3 pi r cubed, and that's the formula for volume of a sphere. So volume of a sphere is 4/3 pi r cubed. So again, you don't have to know how the formulas are derived. You don't have to derive the formula, but I find it helpful to understand how these all relate together. All right, now if we want to calculate the volume of the sphere, again, our formula is 4/3 pi r cubed. Feel free to pause at any time and try these on your own first. We're going to have volume equals 4/3 times pi times 7 cubed, and that gives us 1,436.8 inches cubed. Now, when you're doing this on your calculator, it's really important that you use the pi button. Sometimes in junior high, we just use 3.14. In high school, it's important that we use the exact measurements. And so I want you to be using the pi button and not 3.14. It can cause rounding errors as we have more calculations. All right, for the next example, again, the formula is 4/3 pi r cubed, and volume equals 4/3 times pi. Now, we want to use radius, so half of 21.6 is 10.3. So we have 10.3 cubed. As you can imagine, that's a common mistake, is to misread or misuse diameter instead of radius. And so our volume for this question is 4,577.2 centimeters cubed. And on to our last one, a sphere with a diameter of 2 meters. 4/3 pi r cubed is going to be 4/3 times pi times 1 cubed. So on our calculator, we're going 4 divided by 3 times pi times 1 exponent 3, and this will give us an answer of V equals 4.2 meters cubed. All right, now we're going to take a look at a little bit more of a complex problem. This again is a composite object, and we have a little popper toy here. Now, I remember playing with these when I was a kid. I don't know if you see them as much now, but it was this little toy that you could flip inside out, put on the ground, and it would pop up in the air. My daughter's found a couple of them in the last little bit here that we've had fun playing with, but ultimately this is that popper toy. And so what it is it's just a piece of plastic or rubber or latex, and they have an outside hemisphere, and they've hollowed it out, and so that thickness is what remains. And so the way that we're going to figure out the volume of this object is to figure out what the outside hemisphere would have been and then subtract what part was cut out. So when we're dealing with composite objects, we're either adding objects together, adding the volumes together, or adding the surface areas together, depending on the question, or we're subtracting. So it's either an adding question or a takeaway question. And in this case, it's a takeaway. So if we want to find the volume of the hemisphere, that's half of a sphere. So ultimately what we're going to do is take the volume of the outer minus the volume of the inner. And so we have the outer being 1/2 times 4/3 pi r cubed. Now you could also think about that as the volume of a sphere, 4/3 pi r cubed divided by 2. I tend to multiply more often because I find I'm less likely to forget to do it on my calculator. All right, so 1/2 times 4/3 times pi times 2.5 to the exponent 3 gives me 32.7 inches cubed. Now it's important to note I am rounding on paper, but on my calculator I'm keeping that exact number, and I want to bring that exact number down when it comes to subtracting. Now the volume of the inner object is again going to be 1/2 4/3 pi r cubed, because it's only half of a sphere. 1/2 times 4/3 times pi times 2 cubed will give me 16.8 inches cubed. Now again, I'm going to be subtracting 32.7 minus 16.8. Remember that while I'm writing that on paper, I have the exact numbers on my calculator. This gives me 15.97. If I have to round to the nearest tenth, then it would be 16.0 inches cubed. All right, now that I have my outer and my inner measurements, I can subtract. So I'm going to go 32.7 minus 16.8. Notice again, I'm writing these rounded values on paper, but on my calculator, I'm keeping my answer exact. And that gives me 15.97 inches cubed. If I'm asked to round to the nearest tenth, that's going to give me 16.0 inches cubed. All right, now we're going to talk a little bit about dimensional changes, and I will mention a little bit about conversions at the end, but I will do a separate lesson on conversions for our next lesson. All right, so the question here asks us, what happens to the volume of a square pyramid under the following conditions? Well, we're talking about volume, so I want you to remember that volume is area of the base times the height, and in this case, because it's a pyramid, we're also dividing by 3. That dividing by 3 isn't going to have any impact, so we could even just think about how this would affect a prism. But if the base is changed and if the base is unchanged and the height is doubled, so if I double just the height but I keep the area of the base the same, that's going to double my volume. Now, if I keep the height the same, I keep the height exactly the same, but I double the area of the base. So they don't say double the length of the base, they say double the area of the base. Then again, I'm going to double my volume. Now the question that we're asked most often is what happens if all of the dimensions are doubled? Well, if I double all of the dimensions, think about this with a rectangular prism, length times width times height. If I now double the length and double the width and double the height, 2 times 2 times 2 is 8. So by doubling all of the dimensions, it becomes 8 times bigger. Now there's a way that we can think about this or use it almost as a shortcut. If I'm talking about volume, volume are units cubed. And if I'm doubling it, that means times 2. So doubling would mean 2. Volume is cubed, so 2 cubed is 8. If I were to triple my dimensions, if I was to triple all the dimensions, triple would mean times 3. and volume is cubed, so it would be 27 times bigger. If I were to quadruple it, I would multiply by 4, multiply by 4 cubed, and 4 cubed is 64. So it would be 64 times bigger. All right, now I want to take a real quick look at conversions. Now we have not done a conversions video yet, but I have put a few in the practice. If I wanted to convert from 1 centimeter, let's go with 100 centimeters cubed to meters cubed. Normally when I go from centimeters to meters, I have to divide by 100. But when I'm going from centimeters cubed to meters cubed, I have to do that. I have to convert that measurement for all 3 dimensions, length, width, and height. So if I want to convert from 100 centimeters cubed to meters cubed, I'm going to have to divide by 100, because going from centimeters to meters, I'm dividing by 100, but because it's units cubed, I'm going to have to divide by units cubed. So I'm going to have to divide by 100 cubed. Now, if I put 100 divided by 100 cubed on my calculator, you're going to see something that looks like this, 1e negative 4. Now, you've probably talked about scientific notation in Science 10. This becomes 1.0 times 10 to the negative 4. All right, so if you see that E button, that means times 10 to. And if you wanted to put, for example, 1 times 10 to the negative 4 in your calculator, and you want to shorthand it, you can go 1 times second function, and you're actually looking for the little EE, and on your calculator it looks like a comma, so right above there there's the EE, and then negative 4. And on your calculator it'll look like 1e negative 4. Now, we'll do a couple more conversion questions here. If I wanted to convert, let's go with 25 centimeters cubed, and we wanted to go to inches cubed. Well, on our charts, we know that there are 2.54 centimeters in an inch, so we can divide by 2.54, but it's units cubed, so we have to divide by 2.54 cubed. So 25 divided by 2.54 cubed would give us 1.53 inches cubed. All right, and maybe one more example. If I wanted to take, let's go with 5 meters cubed, and I wanted to convert that to centimeters cubed. Knowing that we're going from meters to centimeters, we have to multiply by 100, but we're going from meters cubed to centimeters cubed, so we're going to have to multiply by 100 cubed, and 5 times 100 cubed will give us 5 million centimeters cubed. So I know those seem like big numbers, but we're not talking about length, we're talking about volume, and that means we're cubing all of our conversion factors. All right, so that gives you quite a few examples on volume. We've also taken a look at dimension changes and conversions, a few practice questions, and then maybe do some questions in your review. Or if you're ready, just jump straight into the review. Have a great day, and we will see you soon.